Okay, let's get started with the Paragon X EM class. Today we're just going to do some extra problems in electricity and magnetism, so extra practice on what we covered in the last 5 weeks. So let's first go over some homework problems. Okay, first problem. There is an infinite cylindrical solenoid with radius r, n turns per unit length, and current I. Okay, draw the magnetic field lines produced by the solenoid. Okay, that's part A. Let's do it first. So magnetic field lines produced by a solenoid. So if we have an infinite solenoid, right? So I'll draw it like this. Uh, we have like just like that, so on. You can think of it as like I have a sort of like a spring here. Let me draw it better. So remember, a cylindrical solenoid, it looks like a spring, except we don't look at the elasticity of the solenoid, and also we're running a current through each of the turns. So, okay, we want to find the magnetic field lines produced by a solenoid. Well, okay, so if my current is pointing in, let's say I put a current uh this way, so it's running, yeah, that way. Then if you want to look at the direction of magnetic field lines, right? So if you use your right hand rule, remember you take your fingers and you curl it in the direction of your current, and then the direction that your thumb points will be the direction of the magnetic field. So here, when I do it, I'm curling it in the direction of the current. My thumb is pointing upwards, meaning that inside the solenoid, the field will be pointing towards like that, something like that, throughout the solenoid. And because it's an infinite solenoid, I can say that the magnetic field lines inside the solenoid, they're all pointing directly upwards, straight upwards. And also, it's a constant magnetic field inside the solenoid. Also, because it's infinite, I can say that outside the solenoid, so in the regions outside the solenoid, so there and so on, there's zero magnetic field. Okay, that was pretty standard. Find the magnetic field due to a solenoid. Okay, remember when we have an infinite cylindrical solenoid, the magnetic field outside the solenoid is zero. So we already know that B, sorry, wait, B out, shoot, wait, B outside of the solenoid, B out, that always equal to zero. Now we just want to find the magnetic field inside the solenoid. Well, okay. Oh, by the way, hi Leo. We're just going over some homework problems uh that was assigned last class. So yeah, if you have any questions, just ask me in the chat or shout it out. All right, so find the magnetic field due to the solenoid. Well, okay. So inside a solenoid, I know that the magnetic field lines are pointing directly upwards. And also outside of the solenoid, there's zero magnetic field, right? We have B out is zero. So if I draw this Amperian loop to like apply my Ampere's law, uh, let me draw it in a different color. So I'll choose this to be my loop. I'll be going in this direction like that. Let me see. Oh, okay, sure. All right, got it, Leo. Uh, all right, so yeah, remember we have our Ampere's law. It was if you have any closed loop, we can do the magnetic field dot onto infinitesimal segment as a vector that equals to the mu zero and then times the enclosed current. So mu zero times I enclosed. Okay, so if I'm going to choose this as our Amperian loop, so like that'll just be the path I do my B dot onto DS on, then okay, so my B dot onto DS, let's do it one component at a time. So over here, um, my path, I'll have, remember, it's in the path, so it'll be going downwards here and to left over here. So at the place where I circled as orange, right? There's no magnetic field because it's outside of the solenoid. So that part, the B dot to DS would be zero. Okay. Now if I'm looking at, oops. Oh, let me redraw that then. That's my ampere loop. So if I'm looking at this section over here, part of it is in a region which has no magnetic field, so outside the solenoid, right? But when it's inside a solenoid, like there's going to be a magnetic field, but still the dot product will equal to zero. Why? Well, that's because in the region over here, so when it gets into the solenoid, the path, your ds vector is pointing to the left, but your b vector is pointing upwards. And remember, dot product, it's always zero if you have two perpendicular vectors. So this path over here and this path over here, when I do the integral of b dot to ds, I'll always get zero. So that leaves us with this path over here that goes, or this segment that goes upwards, right? So I know my B field, my magnetic field that points upwards. Uh, my right, my magnetic field points upwards, and my d acid also points upwards. So this dot product, because B and ds are in the same direction, I can say B times if I let this length be, I'll call that S. So, or wait, I'll call that L. Just not confuse the variables. So B times L would equal to mu zero times the enclosed I, right? And the enclosed current, because every time there's a new turn in the solenoid, there will be another enclosed current. So it will be mu zero times big I, and then times some number of turns of, oh yeah, I'll call it big N, right? So it would just be the number of turns that the solenoid has when I go like when I go up by a length L, right? So if I divide L over, then wait, I'll get mu zero I n divided by L, and you know, big N over L, that's I'm gonna let that equal to N. It'll just be the density of the turns in the solenoid, and that's constant everywhere along the solenoid. So it doesn't matter which path I choose to do this Ampere law on, you'll always get remember this cancels, I'll always get B equals mu zero times the current and then times the density of the turns in the solenoid. That'll be our answer for the magnetic field. Remember, we did this last class, so should be a good review. All right. Last problem. In real life, solenoids have a finite length. Okay. In real life, solenoids have a finite length. Under such a case, sketch the magnetic field lines produced by the solenoid and qualitatively describe the difference between this and what you obtained for part A. Okay, so let's say this solenoid over here was not an infinite solenoid, it's just a finite solenoid. Then I know that when it gets to, like the part where the solenoid ends, I'd expect the field lines to sort of curve outwards. So like they'll be going in this direction. Because remember, magnetic field lines, they always form the closed loop. So if the solenoid is the only, like, it's the only thing in space that we have, then the field lines that are coming out over here, they need to somehow curve back and go back to over here when we had like to the very bottom of the solenoid. So that means that when it comes out of the field lines comes out of the solenoid, it needs to curve outwards and curve all the way down and then back to the bottom of the solenoid. So if I draw the field lines, it will be looking something like that. And remember, this will be the direction. And because it's going to be curving outwards as I get to the end of the solenoid, I know that the field lines inside the solenoid are not going to be, are won't be completely straight. So if I look at a cross section, so these are the sides of my solenoid. Before, our magnetic field lines look something like they were straight. So like that. And yeah, they're basically like straight upwards. But now because it's a finite solenoid, so let's say the solenoid ends here and it ends here, right? So then because outside of the solenoid, it's gonna have the curve like that, like that. Oops. Yeah, it's going to curve back like that. Then when it's inside, it's not going to be completely straight because its pointing will be more curved like this. So you can see it's not exactly a straight line, and that's because it's a finite solenoid. So that's basically the difference between a finite solenoid and an infinite solenoid. So just inside the solenoid, your magnetic field lines won't be completely straight. And outside the solenoid, you'll technically have a non-zero magnetic field because the field lines have to curve back and form a closed loop. Okay, that was just a review of some conceptual details we learned about solenoids. Let's go on to the next one problem. All right. All right, there is a toroid as shown below with inner radius R1 and outer radius R2 and turns per unit length and current I. Find the magnetic field due to the solenoid at a distance of R, small r, where R1 is less than small r is less than R2. Okay, so again, if you use a right-hand rule, and let's say I look at this, I just only look at that current loop. If I use my right-hand rule, I know that the field lines produced by that current loop would be pointing sort of in that direction, right? Because you curl your fingers in the direction of current, your thumb will point that direction. Now, if I have a bunch of those current loops, because that's what forms a solenoid, then the magnetic field lines to that one would be something like that, and so on. So, for example, for this one over here, the field lines would be looking like right at the like right inside of the current loop, right? So that means that if I add all of those current loops together, my total magnetic field would be looking something like this. So it'll be along the circumference of the or yeah, it'll be along like it would basically form a circle, right? That's inside of the toroid. So it'll be pointing in this direction. Use your right hand rule, right? And then, okay, I want to find the magnetic field due to the solenoid at a distance of small r. So, okay, I can see that right now the field lines, it form closed loop and it's perfect circle. And that really like motivates us to use Ampere's law, remember? The B dot onto the ds, and that equals to the mu zero times I enclosed. So I enclosed. Okay, so if I just let my parent loop, like loop I do the integral over just to be like that exact circle with a radius of r, then I'll just have, the B field is always going to be parallel to my ds everywhere along that loop. So then I'll just have B and then times the circumference of the circle, right? So 2 pi r, that equals to the enclosed current times mu zero, right? And what's the enclosed current times mu zero? Well, uh, mu zero times the current and then times the number of turns of the solenoid after I go one full loop. And then so if I do B, I cancel this out, right? Mu zero I n over big N over 2 pi r. And that'll be our answer. If you want to define some sort of density of the turns, so like number of turns per unit length along the circle, then I can just say it's mu zero big I times small n. I notice this is independent of the inner radius R1 and the outer radius R2. But remember, like doing this b dot to ds equals to mu zero I enclosed, the magnetic field lines are only like they only form a circle when you're inside of the solenoid. So it only works if your R1 is less than small r is less than R2. Okay, that's just about toroidal solenoids. Let's go on to the next problem. All right, final problem, homework problem that we need to go over. So a section of a long conducting cylinder with inner radius A and outer radius B carries a current I0 as a uniform current density as shown in the figure above. Using Ampere's law, derive an expression for the magnitude of the magnetic field in the following regions as a function of the distance small r from the central axis. Okay, let's first do small r is less than A. So it just means that, okay, let me try to, all right, never mind. Okay, so it just means that if I'm in this region over here, so in the region where there's no current at all. Okay, well, I have my current, it's flowing like, upwards that way. meaning that all of the currents uh they'll form a magnetic field that's in the plane of the cross section. So if I'm looking at this cross-sectional view, if there was a magnetic field, it wouldn't point into or out of the page. It'll have to point in the plane of the page. Because remember, if I have a current, I do my right-hand rule, the magnetic field is going to be perpendicular to your current. So in the region within the with like in the region that's within the section that has current, well, if I make an ampere loop over here and it has radius small r, then I'll have b times b dot dl, right? So b times uh or okay, uh well, let me just write the integral form for you. Clear all drawings. Okay, so b oops, b onto dl. Okay, that will equal to your mu zero times the enclosed current. But because I'm looking at a like small r is less than a, there's zero enclosed current. So this would equal to zero. And because I know that uh B and DL are in the same plane, I cannot like we don't have that. It's just there's a magnetic field, but it's always perpendicular to my DL. It's just that there's no magnetic field at all. So I can just say, oops, I can just say that in the region where R is less than A, my B would always equal to zero. And it makes sense because you're not enclosing any current. And it's sort of like the shell principle when you have electricity, right? Okay, let's look at part two. It's a bit trickier. A is less than R is less than B. Okay, let me clear this first. So in this case, let's draw another adparent loop. So example, it's like this. This is my adparent loop, and then it has a radius of small r. So this over here, that will be small r. Okay, so if I do the ampere law again, so I have B times 2 pi r by small r, that equals to your mu zero times the enclosed current. Well, what is the enclosed current? That's a bit tricky to find because, we're given that for the entire shaded section, we have a current of I. But because we're enclosing only part of the shaded section, we're only enclosing part of the total I0 over here. So how do we find that total I0? Well, okay, in this cross-section area, I can define some current density. Let's call it J. That will equal to the total current I, and then divided by the total surface area. Like, yeah, the total surface area that's like the shaded region, right? So it just gives J is just the density of the current. So what's the shaded area? Well, it's just pi times uh b squared minus a squared. And then so now I want to find my enclosed I, which only contains like the enclosed I will only contain current over here. So in that region that's within the orange circle. How do I find that? Well, okay, the area of that region that's within the orange circle that has a current, that'll be so the area of that would be pi times like r squared minus a squared. So if I want to find the total enclosed current, I'll multiply. Okay, so I'll do I enclosed now equal to pi r squared minus a squared and then times my current density J, because current density is always constant everywhere inside, like everywhere in the shaded region. So pi r squared minus a squared times like I0, and you'll notice the pi will cancel out, right? So we cancel that pi, b squared minus a squared, right? Yeah, so that will be my I enclosed. It's r squared minus a squared times I0 divided by b squared minus a squared. And I know that this times mu zero equals to my b times 2 pi r. So then divided by 2 pi r. This would equal to my B. So our final answer I'll put over here. B would be equal to and mu zero I times r squared minus a squared, and then divided by b squared minus a squared, and then times 2 pi r. So looks something like this. 2 pi and then r. Okay, so that was part 2. That's when a is less than r is less than b. Okay, so let's look at part 3 now. Uh, part 3 is where r is equal to 2b. Let me erase some of our drawings here just to clear out some space. And that should be good. Okay, now let's go to r equals 2b. So that means that, okay, we're given it's at a point P over here. So that means if I do an Amperian loop that looks like this, that has radius of 2b, then I do my Ampere law, b times 2 pi b, or oh yeah, 2b, right? So it'll actually be 4 pi because my radius is 2b. So times 4 pi b, that will equal to mu zero times the enclosed current. And what's the enclosed current this time? Well, now I'm enclosing the entire current. It'll just be this region over here. And I'm given that the current in that region is just I0, right? So over here, so I can just say mu zero times I0 equals to B times 4 pi P, 4 pi B. So my B would equal to mu zero times I0, okay, divided by 4 pi and times B. And that'll be our final answer. Okay, and okay, that's all for part A. Let's go on to part B. Indicate the direction of the field at point P, a distance r equals 2b from the axis of the cylinder. Okay. Okay, so we're given that in this picture over here, cross-sectional view, we have the current is pointing into the page. So this is the current. I'll draw it as axis. And wait, what does this mean? It wants us to find the direction of the field. Okay, so if the current is pointing inwards, then how do I find the direction of the field? Well, okay, the direction of the field, if I point my thumb in the direction of the current, and then I curl my fingers, the direction my fingers curl will be the direction that the magnetic field curls. So my thumb points into the page, my fingers curl this way, so I'll find that the magnetic field be pointing in this direction. So in circles going that way, meaning that at point P, a magnetic field would be pointing in this direction, tangential to the circle. Okay, so that's just, yeah, the direction of field at point P. Now, what's the electromagnetic forces that are acting on the electron? Okay, the electron is at rest at P. Okay, now remember when we had we talked about the magnetic force, right? So we had F magnetic we had was equal to Q times the velocity vector crosses your magnetic field vector. And what this means is that if you have a charge in a magnetic field, if it experiences a force, it means that you have to first have a non-zero velocity and a non-zero magnetic field. And also, your velocity and your magnetic field cannot be parallel to each other. Otherwise, there will be no magnetic force. In our case over here, our velocity is 0 because we're given the electron is at rest at point P, meaning that it experiences no magnetic force when it's stationary at point P, even though it's in a magnetic field, because it's not in motion, there's no magnetic force. also wants us to talk about electromagnetic forces acting on the electron. You could argue that because we have a current, there's going to be like there's charges moving, and because of the charges moving, there's going to be an electric field created, right? Usually we can just ignore the like we can usually just ignore the electric field due to the currents, because usually it's a small current, and we can say that it's basically a negligible electric field that's caused by these currents. So what that means is that, okay, we have zero uh, magnetic force. We also have a negligible electric force. So the electromagnetic force is acting on the electron would just be F, would we can just say it just equals to zero. All right. Okay, Alvin, I know you just joined, so if you have any questions on any of these things, so just like let me know in the chat. And yeah, so that just concludes our homework review from last week's homework. Let's go on to today's lesson. Yeah, today is just an extra problems day. All right, Alvin, no problem. Okay, good. That's great to hear. All right, today's just an extra problems day. We're just gonna be doing some extra problems to help you review like a lot of the concepts we learned in the last 5 weeks, because it's been a lot of heavy material, so it's good to stop and review. All right, let's go on. Um, Here's a problem about electrostatics. Find the electric field and electric potential due to a spherical charge distribution of radius big R and uniform charge density sigma. I'll just call this sigma. So sigma in all space. Consider both regions within the sphere and outside the sphere. I'll first just draw a diagram for you guys, and you guys can like take a minute to work on this problem. So here's my sphere. And remember, it has uniform charge density, uh, or I'll call it rho. Okay. It has uniform charge density rho in all of space. Um, yeah. So inside the sphere has uniform charge density rho, and want to find the electric field and electric potential everywhere in space. So remember, consider both regions within the sphere and outside the sphere. And it may be helpful for you to remember Gauss's law, which remember it was the integral of E dot onto your infinitesimal dA that equals to the enclosed charge Q enclosed and divided by epsilon zero. I'll give you guys a minute to work that out. Yeah. If you have any answers to questions, just send them in the chat. I'll give you guys maybe another minute to work on the problem, and then I'll start going over it. Okay, yeah, this problem might have been a bit hard because, oops, oh shoot, let me restart the sharing. Yeah, this problem might have been a bit hard because it's a bunch of concepts that you need to be really familiar with. So yeah, that's why we're doing it. Let me redraw the diagram. We have the spherical charge distribution. Uh, yeah, that's our sphere. It has radius big R, and it contains charge with charge density rho. Okay, let's find the electric field and electric potential due to all spherical charge distributions. Okay, uh, consider regions both within the sphere and outside the sphere. Okay, so how we're going to approach this problem first, remember, we can find electric potential from the electric field. Remember, V would equal to the negative integral from infinity to like, some distance R0, right? And it will be like the integral of E as a function R, then dot onto dr. So both of these are as vectors. How we're going to approach the problem is just we'll find the electric field first, and then we'll do an integral to get the uh, electric potential. Okay, let's find the electric field then. So, okay, you might be wondering what does it matter if I'm inside the sphere or outside the sphere? Wait, let's first figure out if we're outside the sphere. So maybe I'm over here and I'm at a distance of, wait, that distance will be r from the center of the sphere. Well, remember, I think might have been in the first or second class, we introduced you to the idea of the shell principle. And remember, the shell principle is that if I have a spherical distribution of charge, such as here, and I'm looking at the electric field that's outside of the sphere, then electric field is the same as if I had just one point charge at the center of the sphere, and it has total charge equal to the the charge of the point charge has the same charge as the amount of charge in the spherical distribution. So what does this mean? Here, if I'm looking at the electric field outside of the sphere, I can say it's the same as if I have just one point charge over here. I'm looking at a distance of r away, and this q would equal to the total charge in the sphere. And what's that total charge? Well, we're given the charge density rho, so we'll have the total charge q equals rho times the volume. So rho times 4 over 3 pi r cubed, big R cubed, by the way, not small r. It's big R because big R, it's the fixed quantity that represents the radius of the sphere. Okay, so that's our Q. And like if we have a point charge, it's pretty easy to find the electric field due to it at a distance of r away. Well, okay, so E outside of the sphere, we have E out that equals to uh 1 over 4 pi epsilon 0, which is basically our k, right? Over 4 pi epsilon 0, and then times our q. which will be 4 over 3 power cubed times the rho. So rho times 4 over 3. Oops. Rho times 4 over 3 pi r cubed, and then divided by the distance to the charge squared. And this time it will be the small r squared, because this one over here, we want to look at the distance from the charge, not the big R, which represents the radius of the original sphere. Okay, so our E out, if we simplify that, we'll get this rho times big R cubed, and then divided by, let's see, be 3 epsilon 0 times R squared. So that's our E outside of the sphere. And we were able to get this because we used the shell principle. So we just reduced this entire sphere to 1 point charge located at the center of the sphere. Okay, I'll erase all the other work so that we can have room for next part. So, okay. All right, let's look at the other, a bit trickier part of the problems. So, wait, hold on. E out. Say E out. Okay. So the trickier part of the problem is finding the electric field that's inside of the sphere. So remember, the sphere, it has uniform charge density rho. So like every part of the sphere, inside the sphere, it's like filled with charge. And remember, we have Gauss's law, right? So we had, let me draw a divider here. So we had integral of closed loop or closed surface integral of E onto the dA. We know that equals to the enclosed charge, so Q enclosed divided by your epsilon 0. Okay, so if I'm looking at a radius of small r that's within the sphere, so my new sphere will look something like this, like this. Okay, if I choose my surface to integrate on as the sphere on the inside, well, my E, right? If I draw the electric field lines, I know it's pointing radially outward, so it'll be looking like this. It's all radially outwards, and they're all parallel to the dA vector, meaning that I can change the dot product just into a scalar product of the two magnitudes. So I know E times the 4 pi r squared, 4 pi small r squared equals to the enclosed charge divided by epsilon 0. But what's the enclosed charge? Remember, it's not the total charge of the big sphere. It's only the charge that's within this sphere over here. And what is that? Well, it'll be 4 over 3 pi. This time, it's small r cubed because I'm only looking at the charge inside of my Gaussian surface, right? So it's 4 over 3 pi r cubed times rho divided by epsilon 0. After we simplify, we'll get E on the inside. E in would equal to rho times R small r divided by epsilon 0, or 3 epsilon 0. This is my E inside of the sphere. Okay, so now we found E inside and E outside. Let's find the voltage. So just be a simple integral, right? Remember we had this integral over here. So we want to find V, okay, V from, yeah, V outside of the sphere, right? So V, let's go, V as a function of R. And remember, this only applies if we're outside of the sphere. It'll be negative integral of that dot to dr. So be negative rho r cubed divided by 3 epsilon 0 r squared. And because the electric field will always be it will always be, wait, yeah, all right. So the electric field and the dr vector, they're all vectors, right? So electric field that points radially outward, my dr would be pointing radially inward. So what does that mean? Well, so so this dot to dr. So E dot to dr it will equal to, in our case, it will equal to negative E times the dr, meaning that this will turn into a plus, right? So it'll be this times dr from or from infinity to some r. And what do we get? Okay, if we do the integral, we'll get rho r cubed over 3 epsilon 0, and then times r to the negative of this, and then evaluate from infinity to small r. What are we going to get? Well, when it's at infinity, it's going to be equal to 0. So we only really care about when it's at r. So just equal to rho r cubed divided by 3 epsilon 0 times your r. Okay, yeah. All right, we're running a bit out of space here, so I'll clear this again. Yeah. Right. So that's our voltage outside of the sphere. Now let's look at the voltage within the sphere. Okay. So if I want to find the change in voltage between a point on the surface of the sphere and some point inside of the sphere, what I'll do this integral over here. So my E in dot into dr. So negative of in dot into dr. So again, it will turn into positive. So rho r divided by 3 epsilon 0 dr, and then from some like big R, because I'm looking at from the surface of the sphere to the inside, so times or to R, this will be delta V within the sphere. Delta V in equals that. And once you do the integral, you'll find it equals to rho R squared. That's interesting. Okay. G, yeah, okay. The sign really doesn't matter, but uh I'll just say that I'll keep it positive because just to keep it consistent with what we had over here. So rho times big R squared minus R squared over 6 epsilon 0. So what does this mean? Well, okay, sorry, I'm sort of jumping around over here, so I'll go over here. Uh, so what does this mean if I want to find the voltage somewhere in space? V as a function of R. If I'm outside of the sphere, then I can just say it's going to be equal to what we got over here. So my rho times big R cubed and then divide by 3 epsilon 0 R, right? But V R, if it's inside of the sphere, then I know it will equal to, so first rho times big R cubed divided by 3 epsilon 0 times small r, or wait, it goes, yeah. So my final small r will be at r. So this one will cancel. We get rho times small r cubed, or sorry, small r squared, or big R squared, by 3 epsilon 0, and then plus I'll have here rho times big R squared minus R squared divided by 6 epsilon 0. Oops. Yeah, and that'll be our final answer. No, it's a bit messy. Yeah, sorry about that. Uh, but yeah, that will be our final answer for the voltage as a function of the distance from the sphere. Yeah, let's go on to our next problem. Uh, we can skip this for now for time's sake. And let's see. Yeah, how about let's do this problem first and we can go back to the original problems that we have time. Okay, so this one's about conductors. Two conducting spheres of radii r and 3r that are infinitely far apart possess charges q and qq initially. Their surfaces are then connected by a conducting wire. When the system has reached an equilibrium, find the final charge on each sphere. I'll give you guys some time to do this problem and we can talk about it. And it will be helpful to remember that if we have a system at equilibrium, then wait, system of conductors at equilibrium, then we know that the surfaces must have equal potential. Otherwise, it will not be at equilibrium. So try to use that fact when you're solving this problem. I'll give you guys maybe a minute to think about this problem and then we'll go over it. All right, I'll start going over this problem. Okay, so let's draw a diagram first. So I have two conducting spheres. One has radius small r, or over here. This one of them is the sphere. Right, they're infinitely far apart, so I'll draw another one here. Has radius 3r, and then they possess charge q and 2q initially. So this one has originally has charge q, this one originally has charge 2q. And then I connect their surface by a conducting wire. So that just means that charge can flow between the two conductors. Wait, when the system has reached an equilibrium, find the final charge on each sphere. Okay, when the system reach an equilibrium, that's really important to notice. What that means is that these two spheres must have equal potential. Because think about it, if this sphere over here had a higher potential than the sphere over here, well, what that means is that, if this is a point of higher potential, you can think of it as like, gravity, right? If I'm on a hill, it has higher potential. So if, I have a bunch of charges on a hill, they're probably going to be rolling down to, uh, like they're going to roll down the hill, right? And you can think of it as if I have higher potential over here, what the charges will do is they're going to flow through the wire to the sphere on the left. And after a while, I want to find like the charges on the two spheres once there's no flowing between the two conducting spheres, which just means that I'm at an equilibrium, right? Because they're connected by a wire, that means that charge can freely flow between the two spheres, and also there's no loss of charge. So when the system reaches an equilibrium, I'll still have a total charge of 3Q for the system. And, it's going to be a really important fact that we're going to use when we're trying to solve for the charges on each of the sphere. Okay, so, we said that each sphere must have equal potential. And also, I know that they're infinitely far apart. What this means is I can neglect uh, the effect of the field due to one conducting sphere on the other. So what this means is that, okay, um, I'm gonna have charges that will be on the surface of this sphere over here. So, there'll be charges on the surface. Now, what that does is that creates an electric field. Now, if I don't want the electric field due to this sphere electric to affect the charges on this sphere, I'll just say that, they're infinitely far apart. So the electric field over here due to this sphere over here, it will be basically zero. So I can just neglect the electric field uh created by one sphere and affecting the other sphere. Like I don't want to include that because if we do, it's going to be pretty complicated. But if we don't, then we can just say that the potential of each of the spheres, so yeah, the potential of each of the spheres, if I say this was Q0 and 2Q0, right? And I say it's Q and this will have like Q1 and Q2, right? So the potential on this one, I know it will be K or 1 over 4 pi epsilon 0, whatever you want to use, K times Q1 and divided by its radius, right? So R, small r, that's its potential. And for this one, I know it's like similar. It's KQ2 divided by small r. But, how can I express Q2 in terms of Q1? Well, I know that the total amount of charge stays the same. So that means that I need 3Q0 minus the Q1. I know that equals to the Q2 because I know Q2 plus Q1 equals 3Q0, right? So that means K times 3Q0 minus Q1 and then divided by its radius, which will be here. I know it's 3 small r. Okay, and we need to equate these two, right? Because we know these are equipotential surfaces when the system reaches an equilibrium. So if we just solve, this r cancels out, the k cancels out, what we just get is 3Q1 equals to 3Q0 minus Q1. And what we get is just Q1 equals to 3 over 4 Q0. And if we just, we know Q1 plus Q2 equals 3Q0, then we'll also know that Q2 would have to equal to 9 over 4 times Q0. And we just solved the problem because we found the final charge on each of the spheres. So this will just be our answer. So just overall, what to do here is, that it's at an equilibrium. So these two conductors, they have to be equipotential. Now, the potential of each of the spheres, I can write it as just K times the charge on the sphere divided by the radius of the sphere. And then I just equate these two together. I make sure that I know like the total amount of charge is conserved. And then I can just solve for the amount of charge on each of the spheres. And, we got our answer. So Q1 is 3 over 4 Q0 and Q2 is 9 over 4 Q0. And yeah, that was a nice problem about conductors. Yeah, if you have any questions, make sure you let me know in the chat. I'll do my best to answer them. Okay, let me erase this and let's go on to the next problem. All right, capacitors. Let me see. Yeah, we can do this. Yeah, let's do this problem. Find the capacitance of a spherical shell with radius r and two concentric spherical shells with radii r1 and r2. And if you do not remember, we define capacitance of some conductor to be the charge of the conductor divided by the potential of the conductor, or the potential difference between two conductors. So it depends. So for part A, you'll be using the potential of the spherical shell. For part B, you'll be using C equals to Q divided by the change in the potential between the two spherical shells. But I'll let you guys try to figure that out. And yeah, let's discuss it in a few minutes. All right, I'll give you guys another minute to think about this and we'll go over it. All right, let's go over it. Let's talk about this problem. So we clear this drawing. So, okay, for part A, we're going to be using the capacitance, right? That equals to, we define it as the charge on the shell divided by the potential of the shell. Well, okay, we know what's the potential of a spherical shell with radius r because we know, like, because of the shell theorem, we can say, like, if it's a spherical shell like this, uh, this is my shell, and, you know, it's like a spherical shell, then I can use the shell theorem and say that the electric field and the potential is the same as if I had just 1 point charge in the center of the shell and has a charge Q. What does this mean is that the voltage would just be Q divided by 4 pi epsilon 0, 4 pi epsilon 0 times your big R. Okay, and charge would just be Q, so C would just be Q divided by will be Q divided by V. So I'm just gonna get 4 pi epsilon 0 times your big R. And that's just the capacitance of a spherical shell with radius R. Yeah, that's our answer for part A. For part B, okay, now it's a bit different. We have two concentric spherical shells, radii R1 and R2. Let's draw another diagram. I have, let me divide this first. That was part A. Let's go to part B. All right, let me draw some two concentric shells. It will look something like this. This is my first shell. This will be my second shell. And they're all spheres, so like that. Okay. Now, all right, I want to find the capacitance. So here I'll define, remember we define capacitance as the charge on each of the spheres, which we'll say is equal because it's a capacitor, and then divide by the change in voltage between the two. Okay, so if I want to find this delta V, so it'll just be the difference in potential between the point on the inner sphere to the point on the outer spherical shell. Well, okay, I want to find the electric field in the region between the two shells. So in this region over here. And by the shell theorem, there's no electric field due to the outer shell. There's only an electric field due to the inner shell over there. And what's that electric field? Well, I know that the E as a function of R would just be like assuming R is between R1 and R2. So I have R1 is less than R is less than R2. ER would just equal to the Q divided by 4 pi epsilon 0 times your R. Okay, or R squared, sorry. So if I want to find the potential difference between the two shells, I'll just do the voltage difference. So V would just equal to, I'll just do the magnitude because The sign doesn't really matter here when we're doing capacitance. Uh, yeah, so from point R1 or radius R1 to radius R2, integral of Q over 4 pi epsilon 0 times R squared dr. What does that equal to? Well, that would just equal to your Q over 4 pi epsilon 0. Once you work out the integral, you'll find it's equal to like Q over 4 pi epsilon 0, 1 over R1 minus 1 over R2. You might get the negative of this. Again, it doesn't really matter when we're looking at the capacitance. So then, right, this is my absolute value of my delta V. So then what does this mean? My C, I know it's equal to Q divided by delta V. Well, then what I'll get is just 4 pi epsilon 0. And then on denominator will be 1 over R1 minus 1 over R2. And that's just my that'll just be the result for the capacitance of two concentric spherical shells and the radii R1 and R2. So remember when we're looking at capacitance, just keep in mind we're doing like we define capacitance as just the charge and divided by the voltage or the change in voltage. So in the first case, we just look at the voltage because it's just one spherical shell. In the second case, we look at the change in voltage between the two shells because it's two shells. So yeah, and remember, you find the voltage from the electric field, and the rest is just simple algebra, and you should be able to work it out. Yeah. Uh, yeah, let's move on to the next question. We can probably do one or two more questions. Yeah, let's do a magnetism question. Oh, maybe not. Oh, wait. Magnetism, yeah. All right. An insulating ring with radius big R has surface charge density of sigma. It rotates in the anti-clockwise direction with an angular velocity omega about its central axis. Find the magnetic field of a point that is at a distance h above the disk along the axis of the disk. So yeah, remember previously we dealt with a problem where we have a current loop and we're given the amount of current on the loop. This time it's a bit different. It's an insulator, so not a conducting wire, but it's spinning. So you can think of it as there's a current, but an important step is to if I have charges that are moving, how do I find the current in terms of the charge density, the velocity of the charges, and also, yeah, the charge density and the velocity of the charges. You want to find the current. And from that, you can use Biot-Savart law to find your magnetic field. So I'll give you guys sometime a few minutes to do this problem. And yeah, we'll talk about this in a bit. By the way, it does say surface charge density, but think of it more as a linear charge density. So like basically per length of the wire, how many charges are there? So you can think of it more like linear charge density. It will help you a bit. Otherwise, you have to take into account like things like cross-sectional area, things like that. So yeah, let's just think of it as the linear charge density for now. Linear charge density of sigma. Yeah. But I'll give you guys a bit more time, and this will probably be our last problem of today. So yeah, give you guys maybe a minute or two. Yeah. All right, let's go over it. First, right, we first want to find the current, and through the current, we can find the magnetic field. Okay, so for current, let's clear everything. All right. So remember, how do we define current? Well, we define current as like, if we're looking at some cross-sectional area, we define current I as the amount of charge that moves through some area and then divided by uh the like some time that goes past. So it's just I equals dq over dt, right? And then if I look at some segment of the wire, so let's just look at, if I zoom in a lot, it kind of looks straight, right? So, okay, this is the place where I'm investigating the amount of charge that passes through. Well, in some given time dt, and if I know the velocity of the charges, then I know that, okay, this is a charge over here. After some time, okay, so yeah, maybe that's called dq, or yeah, okay, I'll just say there's some charge here. And after some dt, it's going to move a distance of v dt, right? So that's just, speed times time, right? And then, okay, I want to find the amount of charge that will pass through this this region over here. Okay, so let me erase this. How much charge will pass through? Well, then in a time dt, uh, you know, the amount of charge that goes through this like over there, it's constrained by the velocity of each charge. And in a time dt, each charge is going to move a distance of v dt, right? V dt. So the the farthest away a charge can be, but it's still like able to manage to like go past this, and I'll count the charge. It will be VDT away. So it will be VDT over here, and all of the charges in this region over here, so all of the charges over here, it's able to go past my barrier over there. So what does this mean? Then the amount of charge that can go through dq now equal to the charge density sigma and then times distance, right? So sigma v dt. And then so if I do dq over dt, which will equal to my current, I'm getting my current equals sigma v because the dt cancels. So this just equals to my current I. Okay, if we go back to my case over like the problem over here, we have an insulating ring that's rotating with some angular velocity, meaning that, okay, if it's an insulating ring, the charges on the ring, they stay stationary relative to the ring. But because the ring itself is rotating, it's as if the charges are moving. So, for example, there's this charge over here. Let's say like there's some small charge over there. After some time, like maybe 1 second, it might go over here. And it's as if charges are moving, right? Because I have one charge here and it moves. After some time, it will move over there. And all across the entire ring, there's going to be charges that are moving in a circle. And I can say that the current produced by that is just sigma times the velocity of each charge. But what's the velocity of each charge? Like I'm not given any velocity. I'm only given the angular velocity of the rotation. Well, if you know from your mechanics days that you have V equals your omega times the radius r of the circular motion, which means that my current I is just equal to sigma times omega r. And now that we have I, we can easily find the magnetic field at this point P. Let me clear the board so that we get some more space. So what do we find? We find that this is just, we have an I equal to sigma omega times R. So it's as if instead of a ring, an insulating ring that's rotating, it's as if we have a conducting current loop. It's stationary, except it has charges moving through it with a current of sigma omega r. So how do we find the magnetic field at point P? Well, we use Biot-Savart law. Remember, we have Biot-Savart law, B equals to, well, okay, equals to like some closed loop integral of I dl crosses, right, IDL crosses the r cat vector, oops, plus the r cat vector divided by r squared. Yeah, it will be this integral. So if I choose to integrate along like the insulating ring, which I'll think of it as a current loop, then I'll have, okay, my DL will always be pointing tangentially. My R cap will be pointing towards P. So in that direction over there, notice that DL crosses R, this will always be like DL crosses R, when I'm doing it, I can say the magnitude is always DL times R because DL and R, the two vectors are always perpendicular. Let me draw it a bit better for you so that you can visualize it a bit better. So this will be my DL vector. This is DL. My R cap will be pointing to P like that. And then this is my right angle over here. Notice they're perpendicular. So if I do the cross product, no, then the result of the cross product will be a vector something like this. So if I draw at the point P, it will be looking like a bit like that for each infinitesimal DL. And once I integrate along the entire loop, then you'll notice that the X and Y components will cancel. All that is left, which will be the net magnetic field, will be pointing upwards. And it makes sense because if you use your right hand rule and you curl your fingers in the direction of current and so on, you get your you get your magnetic field points upwards, the direction of your thumb. So yes, at point P, you'd expect the magnetic field to be pointing directly upwards. So if I want to turn this into just a simple scalar integral, I'll be getting it'll still, yeah, scalar integral. So still a path integral I dl times r divided by, oh wait, no, there's no r because remember the magnitude of a unit vector is always one. So it'll just be I dl and then divided by your r squared. What's your r squared? Well, like if this is h, this is big R, then you use your Pythagorean theorem because it's the right triangle. R squared would be big R squared plus big R squared plus your h squared. But remember, I want to project uh what I got for the magnetic field onto the onto the z direction. And so again, we have two similar triangles here. Uh, this is one similar triangle, and this is the other similar triangle. And if I call this theta, well, I also know that it's equal to this angle over here. That's also theta. So if I want to take it to the vertical direction, I need to multiply by cosine. The z direction will be cosine of theta. Well, what's cosine of theta? Cosine of theta equals to, okay, this is h. This is square root of r squared plus h squared. So cosine theta equals h over square root r squared plus h squared. So this will just be h. And then because we're adding another square root of r squared plus h squared, this will turn into r squared plus h squared to the 3/2 power. And once we do the entire path integral, we'll be getting times 2 pi r, right? Because we're integrating over this entire path. Oh yeah, and by the way, there's an extra, just scaling factor on the outside of the integral of mu 0/4 pi. So my final answer for the magnetic field is just mu 0 divided by 4 pi of, because everything in the integral is constant, I'll just be getting I h divided by r squared plus h squared to the 3/2 power to the 3/2, and then times 2 pi r. So 2 pi big R, and this will further simplify into, because these two will cancel, right? So it'll be mu 0 times I times h divided by 2 mu 0 I h r big R over 2 r squared plus h squared to 3/2 power. And remember what we got for the current I. We got current I equals sigma omega big R. We can further simplify this into mu 0 h times sigma omega r squared, and then divided by 2 times your r squared plus your h squared to the 3/2 power. Just like that. And we have solved this problem. We have found the magnetic field at the height h above an insulating ring that is rotating with some angular velocity omega. And that'll be our final answer for the magnetic field. So remember, when you have an insulating ring, the charges on it are stationary relative to the ring, but if the ring is moving, it's as if your charges on the ring are moving. So you can think of it as there's a current, because current is just moving charge, right? And here we have the insulating ring, it's rotating. So you can think of it as a circular current loop, and it has current that's sigma omega r. We found it's just sigma times v. After you use Biot-Savart law, and when you do the calculation of the integral, be sure that you remember that magnetic field, you'll be getting a vector every time. So once you're doing the integral, you're doing the vector sum. So you have to take into account the parts of the magnetic field that cancel. So for example, here we had the X and Y components of the magnetic field, they all cancel. And we're only left with a magnetic field in the Z direction, meaning that when we're doing the integral, we really need to project like what we got here for the magnetic field, infinitesimal magnetic field onto the Z direction. So we multiply by this cosine theta here. After you do the integral and everything, plug everything back in, you'll get a final answer of your magnetic field, which will be mu zero h sigma omega big R squared divided by 2 times R squared plus H squared to 3/2 power. Yeah, looks like we're about out of time, so we can stop right there. Uh, we did, uh, we didn't finish all the problems that I wanted to do, but that's all right. I'll assign the remaining problems for homework, so you can, just take a look at them on your own free time. And once you're, if you have any like questions about it or you have a solution, you can always just send an email to us or let us know on the Discord, and like we'll try to be quick to answer your question. And yeah, just feel free to ask any questions. And yeah, that just concludes our class today. Please review the recordings from the previous sessions. And yeah, have a good day.